Yeah, so thank you for that introduction. I wanted to recognize some of my teachers. As Joel said, I studied at UC Berkeley. At that time, we had the Loma Prieta earthquake in 1989, and was transformational in my life and my career. Motivated me to come down to UC San Diego and do my PhD. So at Berkeley, I studied with. I took my undergraduate courses with Alex Gordelis and Vitelmo Bertero, two earthquake engineering structural analysis specialists. And then Alex Gordelis advised me to come down to San Diego and study with Frieder Sibley. At UC San Diego, I met this guy from New Zealand, Nigel Priestley. We were doing some very important research in the 1990s. That's when I did my PhD, finished in 98, and then started my career in industry. Worked for 11 years at the firm of T.Y. Lin International with Man Chung Tang and David Goodyear. Got some really good experience there. And then I branched out and switched firms, and I was able to design a bridge for my alma mater, which was a big honor for me. This is the Gilman Bridge at UC San Diego. I'm currently at Sister IBT. We've got Danielle Tassin there, who's a legend in the field of bridge engineering. So when I was asked to do this talk, I was happy to do it. I didn't know that much about NHERI. Of course, that's Natural Hazards Engineering Research Infrastructure, NSF-sponsored program. And it got me thinking to what are the natural hazards as they relate to bridges? So then what immediately popped in my head was Maurice White. I don't know if many of you know who Maurice White was, but he did some incredible work in the 1970s related to natural hazards. He was with this group called, here he is with his research assistants. He was with this group called Earth, Wind and Fire, of course. One of my favorite groups. So that's meant to be a joke. I understand many of you are probably laughing right now, so that's great. I'm going to cover those natural hazards, earth, wind, going to skip fire, but then move along to water. So before we get to the natural hazards, I wanted to talk about the state of the art of bridge engineering technologies to lay the foundation for the talk, and starting at the most basic level with the structural forms. So in bridge engineering, we use three main structural forms, which are arches, beams, and cables. And these three forms exist in nature. There's an arch, there's a beam, there's a cable. They've also been used for thousands of years by bridge builders, going back to the Roman times. There's a Roman aqueduct in France that's still going on 2,000 years old and still standing today. There's a 900-year-old beam bridge in Scotland, a very rudimentary bridge, but basically exemplifies the form that we still use today. And then, of course, the Incas in the Andes have been designing and building cable bridges for millennia. So let's fast forward then about 1,000 years into present times, from about 1970 to present day. I call this the technological revolution of bridge engineering. Advanced computer analysis, high-strength materials, and advanced construction methods have allowed us to design structures like you see here. This is the Millau Viaduct in France that opened in 2004. After World War II, there was a big advancement in bridge technology, including segmental girders. Jean Muller was one of the engineers that came to the US and taught us how to design and build bridges like this. This one happens to be one of the first segmental girder bridges in the US, built in North Carolina in 1982. It's called well, it's in the Blue Ridge Mountains. It's the Linco Viaduct. And it's a box girder concrete girder, which we had been doing since the 50s and 60s in the US, but the difference here is this one's built segmentally, which allows us to build it from above without any false work or any supports underneath. And this is still state of the art as of today. Allows very long spans up to about 800 feet for a girder, and allows us to build in remote locations under difficult site conditions because we can build these from above. Here's a different bridge type. It's actually a hybrid between a cable and a beam system. It's called a stress ribbon bridge. This is used primarily for pedestrian bridges. It's amazing that it can span so long with such a thin structure, 418 feet for this particular example, only 15 inches thick. And that's possible because it works as a cable. It's basically a very flat suspension bridge with the suspension cables embedded in concrete. So you're walking directly on top of the suspension cables. So this form was first used in Switzerland in 1967. And then there were a few examples built in Germany. But it was really perfected in the Czech Republic by Jerzy Strosky. He's been involved with I would say more than half of the stress ribbon bridges built across the world in Europe, Japan, USA, Canada, and elsewhere. This one was the first built in North America. It's in Redding, California, over the Sacramento River. And then we built a couple, actually built 3 of these in San Diego County. I worked with NHERI on one in San Diego. So moving on to long span bridges. This is the state of the art as of today for spans up to about 3,000 feet. It's a cable stay bridge. This happens to be the longest concrete span in the world, with a span of over 1,700 feet between towers. This one just opened 2 years ago. It's the 3rd crossing of the Panama Canal on the Atlantic side. And this one was actually designed in San Diego by the firm International Bridge Technologies. There's a picture of Danielle Tassin, who's the chief technical officer of our firm. And then coming back to the US, here's a pretty big arch, a concrete arch over the Colorado River, right next to the Hoover Dam. This one opened in 2010. It's a spandrel arch, which has been used for almost 100 years. The difference here, or the notable feature here, is the way it was constructed with advanced construction technology. So instead of trying to build a support system underneath for the concrete, what we did was designed it so that it can be temporarily suspended from stay cables until the arch was closed at the crown. You can see here they're building the last couple of segments right before they close the arch, and then all those temporary stays can be removed. So technology, the construction technology is key. How to build the bridge at sites like this is paramount. This one was designed by T. Welling International with David Goodyear leading the effort. So I teach the bridge class at UC San Diego, and I like to show this slide to my students. It's a good example of the historical development of long span bridge technology spanning 3 centuries. So this is a site in Scotland over the Forth River. That first bridge, the red one in the foreground, was built in 1890. That was state of the art back then. It was actually a world record for several years, longest span in the world. And then about 75 years later, the second crossing was built using 1960s technology, 20th century technology. It's a completely different bridge type. Instead of a cantilever or steel truss, it's a suspension bridge using a suspension cable as the main supporting element. And then in 2017, there was a third crossing, this time using the best technology available at the time, once again, cable stay bridge, which is state of the art, the current state of the art, state of the practice. So now I'd like to go to Spain and show a few slides on the Rio Ebro Bridge, which opened in 2011. This one is designed by the firm of Strosky, Hutsey and Partners. And it's modest in size, 820 feet from abutment to abutment, but it's a very elegant, very sophisticated and technologically advanced design using a steel orthotropic deck to keep the deck very light. And then the entire bridge is supported by these 4 cables right down the center of the bridge. You can see how they attach and suspend the main span. Instead of anchoring these cables into the ground as a traditional suspension bridge would do in a heavy concrete anchorage, the main cables are anchored to the deck itself. It's a self-anchored system. So you see how those 4 tendons anchor into the ends of the bridge, and that horizontal force is resisted by compression in the deck. So for any given site, it's important to understand the feasible ways to build a bridge, and the bridge designer really needs to understand construction to come up with a cost-effective bridge design that can be built cost-effectively. Many times the bridge engineers will be working with a contractor to figure out the most economical way to bridge the site. So for this particular example, the 2 ends of the bridge, the approach spans and cantilevers were built with temporary supports on each side of the river. You can see the temporary islands that were constructed there. And then once the 2 cantilevers were complete, the middle portion of the central span was fabricated and put into the water. It's basically a boat shape, so it floats, and pushed into location and then pulled up on winches from the 2 cantilevers of the bridge, and then spliced, and then the central post-tensioning tendons, the main cables were tensioned to complete the bridge. So as the engineers designing this bridge, we need to develop a good model of the bridge and to capture all the stages of construction so that we're certain that all of the stages of construction are going to work. And then, of course, the completed stage, capturing any locked-in effects with a stage construction model, and then applying all the live loads and other loads that are going to affect the bridge during its surface life. So there's a completed structure, a very elegant bridge that showcases the state of the practice, the technology that we have available today. So let's move into the second topic, which is natural hazards. That's what this workshop is all about. And I'm going to cover wind, floods, and last but not least, seismic. So in the US, we design our bridges based on the AASHTO LRFD code. And here's a listing of the different loads that we design our bridges for. In black here, highlighted are the loads from natural hazards, including water loads, stream pressure, wind loads, and earthquake loads. So for wind loads, for most bridges that are small to moderate in size, we do a very simplified approach to wind, where we just apply static wind pressures, typically about 50 psf on the superstructure and about 40 psf on the substructure. For longer span bridges, that simplified approach is no longer adequate. As we all well know, many of you remember seeing these videos of the Tacoma Narrows Bridge collapse in 1940. That was before we had a good understanding of how wind affects the response of long span bridges. So this bridge was redesigned and rebuilt about 10 years later, this time using wind tunnel testing and doing some applying aerodynamic theory. It was more of a brute force approach where a very stiff truss was added to prevent the oscillations of the deck. Today, we would have a more elegant approach where we have more sophisticated dynamic models and more sophisticated wind tunnel testing, and we're able to reduce the effects of wind by using a more aerodynamic shape of the deck. So let's move into water loads and floods. Most bridges cross over waterways, rivers, and so forth. So during times of flooding, we need to be able to resist these water loads, loads from debris impact, and also the effects of scour. This is what scour looks like. It's actually the #1 cause of bridge failures in the US, more so than seismic for sure. And scour is not really a loading, but more of a change of boundary conditions where the foundations may become undermined and unstable. So now let's move into earthquakes. Of course, in California and other seismic regions of the world, seismic is very important loading for bridges. It's most likely the largest loading that a bridge will ever see, and we need to understand how this works. In California, we've learned from 3 major earthquakes: San Fernando in 1971. You can see some of the effects of that earthquake here. Loma Prieta in 1989, and then Northridge in 1994. So what we've learned from these 3 earthquakes are the 3 most common failure modes, and that is unseating of expansion joints, where a complete span could collapse because it's unseated, failure of columns because of inadequate horizontal reinforcement to resist shear and provide ductility, and also improper detailing of beam column joints. So let's go back to UC San Diego. In 1986, the first structures lab was opened, and just awaiting to get some funding for testing. Talk about being at the right place in the right time. 1989, the Loma Prieta earthquake hit, and that generated an influx of funding for seismic testing. Followed up in 1994 by Northridge, created a big backlog of testing. A lot of myself included, and a lot of my colleagues got PhDs doing this research. 94, we opened the Structural Components Lab and the Composite Structures Lab, and then the SRMD facility in 1999 to test full-scale bridge bearings for many of the toll bridges throughout the state. And then in 05, the Engelkirk Center was opened with the outdoor shake table, which is the focus of today's workshop. I'd like to acknowledge the founders of the Department of Structural Engineering: Gil Hegemeyer, Frieder Sibley, Nigel Priestley, and Enrique Luco. These were the professors that started the department and were instrumental in a lot of the seismic research, which changed the way we do seismic design, not only in California, but around the world. We tend to design for larger seismic shaking today than we did 50 years ago. It's a displacement-based approach, utilizing capacity design philosophy. The report that came out in 1901 was instrumental in changing the way that Caltrans assesses bridges. This worked its way into Memo to Designers 20-4 for retrofitting the bridges throughout the state. This textbook came out in 96 based on this research, Priestley, Sibley, Calvi textbook, which is seen as the Bible for the seismic design of bridges. And then ATC 32, which turned into the Caltrans seismic design criteria, which came out in the late 90s, the first version, and was just updated 3 years ago to version 2.0, but it's still largely based on that work that was done in the 80s and 90s at UC San Diego and other research institutions. So we tend to treat ordinary bridges different than important bridges. Ordinary standard bridges are covered by the SDC, and we rely on ductility. We design for really just one design level earthquake, which is roughly a 1,000-year return period. For important bridges, that it could be either a lifeline structure or a major crossing like the Bay Bridge you see here. It's project-specific design criteria is established many times with a multi-level approach, where we're looking at small earthquakes where there should be no damage, medium-sized earthquakes where there can be damage, but you need to be able to open the bridge immediately after the earthquake, and then very large earthquakes where we're looking at preventing collapse. So now let's move into the research needs, and the focus on the research needs is also based on the wind, the floods, and seismic. I reached out to Caltrans a few weeks ago to get a handle on the types of research that Caltrans is doing, and they sent me some of their catalogs of the recently completed research as well as the ongoing research, and I've summarized it here. Caltrans is still spending about $25 million a year on bridge research, and most of it is still seismic research, where they're looking at the response of abutments, foundations, soil structure interaction, columns and substructures, superstructures, analysis methods, reinforcing details, isolation and dampers, and assessment and monitoring. They're also looking at other topics, including accelerated bridge construction. This is an important topic now because many of the bridge projects that we're doing are in urban areas where we're widening or replacing a bridge over traffic, and it's important to get in and get out quickly so we're not disrupting traffic for years on end. So ABC is an important topic. Some of this ABC research is related to seismic to make sure we can get good seismic performance out of these precast systems, looking at pre-stressed precast girders, bridge decks, and other effects. Going back to the flood hazards and scour, I can see this is a potential research topic. It's not really a structural issue. It's more of a topic for our colleagues in hydraulic engineering. But if we can develop better ways to reliably assess scour, many times the current tools that we have provide scour depths that are I believe to be unrealistically large. If we had a better way to assess scour depths that could save some money in terms of the construction of our new bridges. Also, ways to reduce scour with more streamlined pier shapes and other hydraulic devices that could reduce scour. Moving into structural engineering and concrete, creep drives the design of our cantilever bridges, our segmentally constructed cantilever bridges, where they begin as cantilevers and then they turn into continuous beams once we close the midspan, and then creep takes over. AASHTO and ACI don't adequately address the way that creep works. It can be unrealistic and many times unconservative. You can see the graph here is comparing the AASHTO and ACI creep curves to the Eurocode, where the magnitude is different as well as the shape. The Eurocode addresses the long-term creep. You can see that slope increases over the long term, where it's rather flat for AASHTO and ACI. So that's a potential source of new research to get us where we need to be in terms of concrete creep. And then for seismic, the trend or the current codes use ductility, which is a good economical way to design our bridges for collapse prevention and to save lives. The downside is that many of these bridges will be damaged beyond repair after a big earthquake, meaning that we may have to go in and replace a lot of the damaged bridges, even though they performed well up to the current standards. We could do better potentially if we start to investigate ways to prevent damage with elastic systems. And that can be either foundation rocking could help with that. where we allow foundations to rock to reduce structural damage. That's a potential area of research using the new shake table, and also using unbonded pre-stressed tendons in columns so that we have less damage after an earthquake. These systems self-center and they reduce damage. Here's a slide that Professor Restrepo shared with me showing two-column bent that they tested with unbonded tendons, and it performed very well, self-centered, very minimal damage after a big earthquake. So these are the systems that I'm talking about that I think is the next generation of seismic design. We need to do more research to prove that these systems are reliable and robust and will work well, can be implemented in the field. Also would like to address reliability and robustness in terms of bridges. Unfortunately, in the past few years, we've had several bridge failures going back to 2007, the I-35W bridge in Minneapolis that collapsed based on well, it was a non-redundant system. It was a truss, and it had undersized gusset plates, and then combined with some construction loading, led to the collapse of that bridge you see there. In the foreground, you see the older concrete arch behind it. And then moving on to the FIU bridge, which was a non-redundant concrete truss that collapsed in 2018 while it was under construction. That was the cause of that was poor detailing of a joint. That one is still under investigation. And then we had a cable stay bridge, a very early cable stay bridge that was non-redundant. You can see there's only one cable instead of a whole plane of cables that collapsed in 2018. So this comes down to reliability, robustness, redundancy, how the code handles this. I think there's a lot of room for research there to prevent future disasters like this. But reliability and robustness also deals with durability and maintenance. Here's an example bridge in Stockton that was built in 1972 that most likely needs to be replaced. It's not in danger of collapsing, but it's become a maintenance issue. This is a state-owned bridge that Caltrans is spending millions of dollars each year patching the deck. And what led to this poor performance has to do with actually fatigue of steel. So it's a steel girder bridge, and it's braced with these pipe braces. After many cycles, the bridge is 48 years old. I don't know, about 10 years ago, they started to see fatigue cracks in the braces, where some of them just completely failed, leading to more flexibility in the girders. So the deck is deflecting more, and it's a lightweight concrete deck, which is prone to spalling. So the deck is spalling and cracking, and Caltrans it's just turned into a money pit in terms of maintenance. So some other potential research topics dealing with fatigue and durability of bridge decks, and also understanding when to use lightweight concrete. Those are also some potential research topics on the bridge side. So with that, I'd like to go ahead and stop and thank you for your time. And if we have time, I can answer some questions.
Thank you very much, Tony. Thank you very much for your very interesting presentation.
Great, you're welcome.
I think there is let me read the question. What is the state of the practice in bridge seismic design or performance-based, considering the soil foundation bridge interaction?
Yeah, so for most bridges, most bridges tend to be small to moderate in size, and we would call that an ordinary bridge, one that's not important if it's has spans less than 300 feet, and we would consider it a standard bridge. And for that, in California, we follow the Caltrans STC, which is It's a very simple approach. Bridges tend to be simple. A lot of times you can simplify these into 1 degree of freedom oscillators, and we rely on ductility. We'll do pushover analyses. Well, we do response spectrum analysis to figure out the displacement demands, and then we do nonlinear pushover analysis to verify that the performance is going to be there. So that's done for the vast majority of the bridges. In California, other states do similar approaches. When we get to a major bridge, major crossing like the Bay Bridge, it's a totally different approach. The philosophy is similar, but we go to nonlinear time history analyses and really spend a lot more time understanding the seismic response. Many times with geotechnical engineers working alongside the structural engineers to develop the time histories and also modeling the foundation systems with PY curves for the soil springs and so forth. But the approach is still similar, where we're finding the seismic displacements and then doing pushover analyses to make sure that the response is going to be stable and going to meet the design criteria.
Thank you very much. There is another question. Let's take one more question. With regard to the large number of old bridges in California, do you think the industry is currently equipped with tools from research to understand performance of old bridges and retrofit them?
Well, this is what the topic of this slide is. There's a lot of old bridges that are starting to see deterioration in mainly the decks. The decks get beat up because you have heavy loads driving on them. There are needed deck replacements or overlays. Some of these present challenges, especially if it's a post-tension bridge where the deck is part of is resisting compression loads from post-tensioning. So how do you replace a deck on a post-tension box girder bridge? So I think advancing the technology in terms of how to repair bridge decks with overlays, with advanced materials, there's a lot of room there for research to show that to come up with ways to repair these aging bridges.